In a truly breathtaking turn of events, astronomers have recently made one of the most astonishing discoveries in modern cosmology. Somewhere in the vast, almost unfathomable expanse of the universe, scientists have identified gigantic cosmic structures. Structures so enormous that they exceed the size of our own Milky Way galaxy by more than 100 times. Their immense scale is difficult to put into words. Even the most seasoned experts are left in awe by these formations. This discovery doesn't just add a new piece to the puzzle, it shatters the framework we've been working within. It fundamentally challenges our previous understanding of how the universe is organized, how structures form and evolve, and how far human knowledge has yet to go. Trying to fully grasp the sheer magnitude of these formations is, for most of us, almost impossible. The numbers involved are so huge they start to lose meaning. But one thing is clear. These are no ordinary galactic clusters. They belong to a scale of structure that operates far beyond anything our own galaxy can claim, and they force us to reevaluate how we think the universe grew from the Big Bang to what we see today. Among these titanic formations are the Bootes superclusters, which gain their name from their proximity to the Bootes void, one of the most extraordinary and least populated areas in the cosmos. This void was discovered in 1981 and is located about 700 million light-years away from Earth. It's a cosmic cavity spanning roughly 300 million light-years in diameter, a vast region of space with far fewer galaxies than expected. Situated near this void are two known superclusters, each lying approximately 1 billion light-years from Earth. The first is estimated to be about 830 million light-years away, and the second lies slightly farther behind, but at a similar distance. Although these superclusters haven't yet been studied in complete detail, early findings suggest they're significantly more massive and expansive than our own Virgo supercluster, which itself includes the Milky Way. The very existence of these Bootes superclusters in such a sparsely populated region of the universe is perplexing. Why would such massive structures form near a void with so little matter? The Bootes void was originally identified by astronomers Robert Kirshner, August Ermler, and Paul Schechter in 1981 during a galaxy redshift survey. Their observations revealed a shockingly low density of galaxies in the region, prompting years of follow-up studies. While astronomers have since identified several thousand galaxies within the void, the number remains small compared to what one would expect in a region of that size. It suggests that large swathes of this area are still largely unexplored and may hold countless hidden galaxies, perhaps even ones unlike those we've seen before. One of the most recent and compelling additions to our catalogue of massive cosmic structures is the Saraswati supercluster. This enormous concentration of galaxies was discovered by researchers at the Inter-University Center for Astronomy and Astrophysics. The supercluster spans a jaw-dropping 600 million light-years across and contains a mass equivalent to more than 20 trillion suns. This places Saraswati among the most massive and expansive superclusters ever identified. In fact, so few structures of this scale have been found that Saraswati stands in rare company, alongside giants like the Shapley supercluster and the Great Sloan Wall. What truly sets Saraswati apart is its incredible distance from Earth. It lies nearly 4 billion light-years away. For perspective, that means the light we see from Saraswati today has been traveling through space since the universe was only about 10 billion years old. It is the farthest structure of its kind we have ever observed. Even the Shapley supercluster, often cited as one of the largest known structures in the nearby universe, is roughly 8 to 10 times closer to us. Researchers uncovered Saraswati using data from the Sloan Digital Sky Survey, revealing a structure containing at least 43 groups and clusters of galaxies, with around 400 individual galaxies identified so far. Another remarkable structure is the CFA2 Great Wall, often referred to simply as the Great Wall or the Cosmic Wall. Discovered in 1989 by Margaret Geller and John Huchra, this immense filament of galaxies stretches between 500 and 750 million light-years in length. It is roughly 200 million light-years wide and about 16 million light-years thick. This wall houses 3 particularly massive superclusters, Hercules, Coma, and Leo. Yet, even with such detailed observations, we may not be seeing the whole picture. Much of the Great Wall may be hidden behind what is known as the zone of avoidance, a region of the sky obscured by the gas and dust of our own Milky Way galaxy. This zone of avoidance makes up about 20% of the observable universe and presents a major obstacle to astronomers trying to map the cosmos in visible light. At optical wavelengths, the light from distant galaxies is blocked, making it difficult to know if structures like the Great Wall extend even farther than we can currently detect. However, modern techniques using X-ray and infrared observations offer hope. These methods can penetrate the dust and gas, slowly revealing more of what lies behind this galactic curtain. According to the standard model of cosmology, these vast structures are thought to form along filaments of dark matter. These filaments act like the scaffolding of the universe, weaving together a vast cosmic web that spans billions of light years. Though dark matter cannot be seen directly, its gravitational pull shapes the motion and formation of galaxies. It's this invisible framework that determines where matter collects, forming the enormous galactic walls, superclusters, and filamentary structures we observe. Another mind-boggling structure is the Colossus supercluster, which was first noted during studies in the 1980s. It extends over a colossal distance of about 910 million light-years. For comparison, the Laniakea supercluster, which contains the Milky Way and was once thought to be among the largest structures, measures about 520 million light-years across. Colossus is roughly 1.7 times larger. It is home to numerous galaxy clusters, groups, and both giant and dwarf galaxies. Its total mass is estimated at a scale of 10 to the 29th power in solar masses, making it one of the heaviest structures ever mapped. In 1987, another significant structure was identified, the Pisces-Cetus supercluster complex. This structure is particularly notable because it includes our own Virgo supercluster and therefore encompasses the Milky Way itself. Stretching over a span of 110 million light-years and holding an estimated mass of 10 or 18 solar masses, it ranks among the largest and most massive formations in the known universe. The complex is composed of 5 key regions: the Pisces-Cetus supercluster, the Perseus-Pegasus chain, the Pegasus-Pisces chain, the Sculptor region, and the Hercules supercluster. Additionally, it connects with the Laniakea supercluster and the Hydra supercluster. This complex has been named after its richest components, including the Perseus-Pegasus filament, which itself houses the immense Perseus-Pisces supercluster. The Perseus-Pegasus filament is an enormous structure extending approximately 1 billion light-years from Earth. It's often regarded as one of the largest known filaments in the cosmos. Some early mentions of this filament trace back as far as 1936, when Clyde Tombaugh was conducting research in search of trans-Neptunian planets. Later, parts of this structure were also noted by Walter Ever in his own observational data, adding to the historical context of its discovery. Finally, we come to the Boss Great Wall, a supercluster complex uncovered in early 2016 through data collected by the Baryon Oscillation Spectroscopic Survey. This incredible formation stretches roughly 1 billion light-years across and contains a multitude of galaxies, some clearly visible and others obscured by interstellar dust. Its total mass is estimated to be around 10,000 times that of the Milky Way. Although its exact boundaries are still under investigation, it is undeniably among the largest structures ever detected. A major point of debate among scientists is whether these massive supercluster complexes, like the Boss Great Wall, are gravitationally bound and moving as single units, or if they are slowly drifting apart as the universe continues to expand. On the largest scales, the universe is believed to be structured as a web of filaments and voids. These filaments, which make up the cosmic web, are the densest regions, filled with galaxy clusters, while the voids represent the vast emptiness between them. Superclusters like these, especially ones that are densely populated with high-mass galaxies, offer astronomers invaluable opportunities to probe the origins of cosmic structure, test the accuracy of our models of dark matter and dark energy, and better understand how gravity has shaped the visible universe from its earliest moments to the present day. These discoveries push the boundaries of what we thought was possible. They remind us that, even after centuries of stargazing, the universe continues to surprise us, with ever larger, ever stranger structures waiting just beyond the edge of our comprehension.